Fun fact, black holes actually shrink thanks to Hawking radiation. Stephen Hawking found that black holes might very, very slowly shrink and give off radiation. Now, to try to explain Hawking radiation takes a lot, and I'm going to try my best, but it requires a good understanding of quantum field theory and quantum mechanics. In quantum field theory, the vacuum of space is actually not empty. It is made up of all sorts of fields and energy, and they can come together and manifest in particle-antiparticle pairs. These particle-antiparticle pairs are always coming into and out of existence. When they collide, they eliminate each other, and also, it importantly, allows for the idea of negative energy. Now, black holes are very, very dense gravitational masses that not even light can escape the spherical event horizon. Now imagine these vertical particle pairs, so a particle and an antiparticle, are formed on the edge of the event horizon. So instead of demolishing each other, one actually escapes and the other one goes into the black hole. For us as an outside observer, we would now see an actual particle coming from that black hole. But where would that energy come from? We know that energy cannot be created or destroyed. That's the first law of thermodynamics. The energy came from space-time, but it still appeared to come out of nowhere, which means that the energy going into the black hole must have been a negative energy, and therefore the black hole essentially is losing mass. Here's a great diagram of this Hawking radiation. You'll see here these virtual particle-antiparticle pairs, and one may fall in while one gets to come out. This is the Hawking radiation, these energy particles. Now, this radiation is very, very faint and small and slow, so our current telescopes aren't strong enough to detect any of it. Now, the radiation temperature, also called Hawking temperature, is inversely proportional to the mass of the black hole, which means that the smaller that it is, the faster and bigger and more radiation it's going to emit. Now, if you have a small enough black hole, it's going to emit this radiation so much faster that it's going to lead to one final burst of intensity with high energy radiation. Now, no such bursts have been detected yet, but it's a really great thing to look for. Hopefully, in the future, we can measure one of these bursts or get a telescope strong enough to directly measure Hawking radiation. But until then, it remains largely as a theoretical model that is largely accepted. Isn't that interesting? Isn't that fun?